Been asked to host today's webinar, and it's my great pleasure to welcome Ulrik Egede from Monash University. Ulrik actually is a long-standing friend of Australian particle physics, going back to the 1990s when he was a graduate student. I met him at CERN. So he's moved to Monash in the relatively recent past, previously being at Imperial College. And he's brought a new experimental effort in flavour physics, and specifically B physics, to Australia through his membership of LHCb, which is a very, very positive development, and one that I think the experimental community is very happy to see. So this afternoon he's going to give us a presentation called Disentangling Possible New Physics in QCD penguin decays, and we look forward to it. So I think if people could mute in general, but I think if they would like to stop and Ulrik can ask questions, I think he's probably happy to be interrupted. So either speak up or put your hand up in Zoom, and I'll try to notice that there's a question if we have one. So on that note, Ulrik, I'll hand over to you, and we'd be pleased to hear your webinar.
Okay, thank you very much. You hear me okay?
Yes.
Okay, good. Okay, yes, so I'll talk about disentangling possible new physics from QCD in penguin decays. So first, to set the scene a little bit, let's just remind ourselves about what in recent years has become known as the flavour anomalies. And this is something that is going back almost a decade now. That we've seen a large number of experimental measurements coming out where there is not a very good agreement between what we predict, given the standard model parameters, and what we actually see. I think maybe as a bit of a surprise to the community, these things have not come out in the CP violation measurements, which was probably what was thought if you go back 15 or 20 years ago, but has actually come out in what we call penguin decays. So the decays where we have seen these anomalies are in the semi-leptonic decays, so leptonic decay like Bs-mumu and semi-leptonic decays like B0 to K star mu. I'll come back to many of these plots that you see on the right here before, but just to give you somehow a taster of what we're looking for here is that if we combine a number of different measurements as is done in this plot here, and we in some kind of space look for, does this fit together to the standard model prediction? In this plot here, you have the standard model prediction sitting at 0.0. And when you combine all these measurements together, you get a best fit region, you get a number, you get an agreement with that region sitting around it, and you can look at how compatible is that with, for example, the standard model. And what you see in one of these, in the specific plot I picked here, from the group around kinematic, we see a discrepancy with the standard model, which is actually above 5 sigma. So that, of course, sounds amazing. You might say, more than 5 sigma. Well, that's it. That's a new physics. We've seen it, that it fits into the conventional requirement for what we can call an observation of something new. But what you see in this here was I picked the slide from the experimental closing talk at the LHCb conference last week by Andreas Höcker. And we were talking about the anomalies in that one. And the conclusion he did after looking at the results was he said, there's only one firm conclusion from this, which is that more data is needed. So that naturally raised the question then, isn't 5 sigma the golden standard for observation? Why do we need more data to convince ourselves that there is some new physics here or not, indeed? And the answer to that really lies in QCD. And that is very much the underlying reason for any debate about the significance of these results. In general, we pick for analysis, we pick the case with leptons in because they do not see QCD, they do not feel the strong force. But nevertheless, there's of course lots of QCD going on in these decays. And when we have anything that goes on in QCD, which is that energy scales of lambda QCD are lower, so at 300 MeV or whatever, we can no longer use perturbative calculations in QCD. So where do we have that? We have that, of course, in the confinement of the initial state hadron. That's non-perturbative. We have it in the hadronization process for the final state, or at least the hadronic part of the final state, which is non-perturbative. And of course, we also have all the interactions with the QCD vacuum going on here. So in general, what we have is that we have something that initially looks like a easy thing to calculate in the standard model, but in reality turns out to be very difficult because we do not simply have a single Feynman diagram we can calculate. We do not have a perturbative process where we can just in a prescriptive way calculate it to a higher position. So there are tools to deal with this. There are tools available such as heavy quark effective theory. We can use what's called line code sum rules, and we can use lattice QCD to provide us some of the answers to that. I'll go through some of that, but my aim is not to give a theory talk, but more to talk about the interplay between theory and experimental measurements, which is so relevant for these measurements here. So the question that I would like to address in this seminar is basically, can we disentangle new physics in heavy flavor decays from QCD effects in the standard model? So will we ever be able to tell these things apart? So in particular to that, do we need more data to do this? Or do we need more theory? Maybe I should have written better theory instead. Or should we just give up and say it doesn't actually help that we get these things because there are some fundamental problems that means that we can never draw any firm conclusions from this? So that's basically the question that I hope to be able to address by the end of this seminar. So let us take a step back from that and look first at the language we're using for describing these decays. So the way that we're using an effective theory for describing them. So in general, all these decays we're considered with here are what we call flavor changing neutral current decays. So these has in the standard model to happen at the loop level, because what we have is if you look at the decay over here to the left, where we have a B that goes to a K star and a pair of muons, then we have a B to S quark transition. The B and the S quark, so of course, have the same charge, and we do not have flavor changing neutral currents in the standard model. If we emit a Z, it cannot couple to the B quark and the S quark at the same time. So in the standard model, the lowest order way this can go on is through a loop like what we have here. We can then reshape this diagram here. If we took, for example, just the S quark in the final state and flipped over to an initial state instead, then you would have the diagram for Bs to mu. So therefore, it's the same physics that we are addressing in those. However, everything does not need to go through the weak force for these decays here. So if we stick to the standard model here, then looking at the diagram to the right here, this is an illustration of where we get QCD involved in this, and I'll come back to that, which is that we can also create CC bar states from this here. So we get a B to C transition instead, but then this CC bar loop, as we have here, can then radiate a photon that can then couple to mu plus mu minus, for example. So we can also reach the same final state without having an electroweak penguin diagram as we have to the left. And that's really where the trouble starts in terms of calculating things. So that, of course, is in the standard model. We can ascribe things, of course, also from new physics. So new physics contributions can, for example, be at tree level. So one thing you could have is that you could have, for example, a leptoquark model. A leptoquark is something that carries both lepton and baryon number. So if you look at this one here, the K star is not quite aligned in the right place of this decay here, because you actually see that the S quark actually comes from the other end of the leptoquark here, but we end up with the same final state again. So we can have decays like that at tree level, or you could potentially have a new vector boson, a Z prime, which is not where it's not disallowed that it couples to to a B and an S quark at the same time, so we can get flavor change in neutral currents at tree level there through such a new physics contribution. New physics contributions could of course be at loop level as well. There's nothing that prevents that. Or you could even have both possibilities and so on. So there's many options here, but that of course, just because it's possible doesn't mean that it is how nature looks like. So when we describe these decays here, everything that happens inside these loops, or indeed at the tree level, both in the standard model and from new physics, happens through interactions with particles that are much heavier than the B-meson or any of the final state particles. So the W is much heavier. The new physics particles we're discussing here will be in the multi-TeV mass range as well. And that means that we can treat the decay in an effective theory. So the only thing that we really observationally can see is that we have a 4 fermion operator, as illustrated with the red square here, that simply couples the B quark, the S quark, and a pair of leptons together. So this is exactly the same as we do when we treat radioactive decay as a 4 fermion operator in Fermi theory. There's no difference to that. So we are not sensitive to exactly the nature of what new physics might be there. We're simply sensitive to the structure of it. So the way that we do this is that we describe these different couplings by creating an effective Hamiltonian. That effective Hamiltonian will have standard model in it as well, and then it will have a parameterization of new physics effects in it. So traditionally, there's a number of terms we just take outside here, as you can see in the sum of the top here. In this one here, that's just by convention that we do that. And then you see a sum here over different types of couplings here. In this one here, we have the operators here, and we have what we call the Wilson coefficients in front of it. So the Wilson coefficients are really the ones that determine how much do we have of a specific type of coupling. In that sense, they take the same role as G Fermi does. What are the types of couplings that we have an interest in here? There are couplings that we call C7. So that's couplings of the magnetic dipole operator. So they're the ones that will emit a photon. So that will be responsible for decay like B to K star gamma, for example, but also a decay like B to K star mu mu, where we can have a virtual photon that goes to the muon pair. We will have semi-leptonic operators. They're the ones we call C9 and C10. And we have in the middle here, there are 2 different ones. So C9, which is a vector coupling. So you can see we just have a gamma mu in it here. And we also have an axial vector coupling, the gamma mu, gamma 5 down here. And we finally have a scalar operator, which however, in most of the decays I'm talking about today, are very suppressed. You will also see here that we have some primes on them here, on C7, C9, and C10. They are related to if it is a left-handed or right-handed operator. So they go together with the left or right-handed projection operator we have here. So in the standard model, the decay is effectively described by the electromagnetic coupling here, the C7. It's described by a value for C9 and a value of C10, which have the opposite sign, more or less corresponding to the V minus A theory for weak decays. So that's what we have in the standard model. We have a C9 value, we have a C10 value, which are almost opposite in sign. And then the primed values, which are the right-handed couplings, are 0 in the standard model. So what we want to do is we want to make experimental measurements, and we essentially want to determine these Wilson coefficients, and then we want to see if they then agree with the standard model expectation or not. So what do we need for that? We need a number of form factors. The form factors effectively describe the hadronization into the K star in the final state we have here. And then we can take the Wilson coefficients that we can calculate in the standard model. we know all the parameters of the standard model to do that. So we can basically calculate the values of C9, C7, C9, and C10. However, what then happens is that we then get what we call factorizable corrections to this. So by factorization here, we essentially mean that we can treat the muon system up here as being something that's completely independent of what happens to the hadronic system down here. So those form factors have, over the past 15 years or so, has been given a great amount of thought. Calculations of those have progressed a lot. They can be done either within light cone sum rules. They work very well when there's a low energy transfer to the dimuon system here, what we call Q squared is low, or they can be calculated in lattice QCD. That works on the other hand when there is a very high energy transfer to the dimuon system here. Those two calculations, they can even be compared now. They have an overlap in regions, and the calculations are actually in very good agreement. And in general, the uncertainties is at the few percent level, and there's also a good confidence in that uncertainty. Unfortunately, we also have what we call non-factorizable corrections. So in this case here, this illustration here, remember again, all these effects here might happen with energy levels below lambda QCD, so we can't really draw them as Feynman diagrams like this here, but it's nevertheless good for our understanding. But in this case here, we no longer have the factorization applying. The system up here that's responsible for creating our dimuon system is no longer isolated from the rest of the hadronic system. We can look at the size of this effect in other hadronic decays. We can make an estimate of this, say this is probably order 10% compared to the other effects we have and so on. But it is something where there is an element of hand waving involved. And that is one of the problems, that we cannot really calculate just how important are these effects here. And then finally, we have the really complicated ones, the ones that we call the charm loop corrections. So these can correspond, for example, to a real physical transition. We have a B0 that goes to a CC bar resonance, a J psi, for example, and a K star, and then the J psi decays electromagnetically to a pair of muons. But there's no need for this CC bar system to be on the mass shell. We can, in principle, have contributions of this at all levels. So these are difficult to deal with. It's not entirely obvious how experimental data should be used to get a handle on the effect of this here. I'll talk about some of the methods later. It's not obvious how the uncertainties can be assessed, and there's in general a big disagreement on that. So this here is really one of the core places where you see why there's not kind of a general consensus that new physics have been discovered in these decays, despite that there are fits that indicate a very high level of confidence in that. And that is in general because these effects here is very hard to say they will be below a certain value. So that now sets the background a bit for measurements, talking about what measurements do we actually have there. So as I said already earlier, in general, we look at measurements that contains leptons to improve the theory predictions. Any of these new physics effects here, or at least almost any of them, would have effects on purely hadronic decays as well. It's just that our standard model prediction for those are so much poorer that it would be difficult for us to come up with places where we could actually say this is not just the standard model. So I'll talk a bit about electroweak penguin decays, particularly the B-K plus mu-mu and the B-K star mu-mu decays. And I'll talk about lepton universality decays, where we are comparing decays with muons in the final state and with electrons in the final state. So if we take a look at one of these decays here, let's look at one of the simple decays first. Let's look at the B plus to K plus mu-mu decay. So the loop diagram in it, the one we have seen already, so the penguin diagram, that one also interferes with the tree level diagram where we have a B to C quark transition, and then the CC bar state that we can form can then subsequently decay. electromagnetically to mu plus mu minus. So what you see in the illustration over here to the right is you see kind of how the differential decay rate looks as a function of the mass of the dimuon system squared, so what we call Q squared here. So what we see in it, we see some huge spikes here that corresponds to the J psi, so first CC bar resonance. We see a spike compared at the psi 2s level, and then we see a number of wiggles out here, which are kind of coming from higher CC bar resonances. The broad thing we see down here, that's what we get from the penguin decay. That's what we're really interested in. But of course, these are also interfering with each other. So I should just say that this plot here, the diagram here, is actually for B2K star mu, where we then get a pole from the photon as well, that we don't get in B2K mu. So how can we write this down? If we try to look at what is the differential branching fraction, so this here, the d gamma dq squared here, is exactly what we had the illustration of on the previous slide. So we can write down what that actually is in our theory. So what we notice here is we notice that we have the Wilson coefficients here, how much we have in these. You can see we have some terms here that are proportional to C10 squared, and we have some terms here that are proportional to C9 squared. We do not get any interference between these because one is a vector coupling, the other one is an actual vector coupling. So in general, the total decay rate we get is actually proportional to C9 squared plus C10 squared. There's a suppressed term from C7 here that we can ignore for just the talking about here. But what you also see is you see that each of the C9 and the C10 terms comes together with these Fs here, which are the form factors. So we have to rely on the theory to predict the form factors. We cannot measure the Wilson coefficients independently from the form factors. They always come together like this here. So far as it's written down here, it looks like that we just have the penguin decay here. But what you can do is you can effectively incorporate the effect of the charm loops into the C9. The charm loops will all, because they couple to mu plus mu minus, will all be vector resonances. So therefore we can put them into C9 as a C9 effective. And what we've done in some of our analysis is we basically put it in as the C9 value that we get from the penguin decay and from potential loop physics. And then the charm loop effect we model as a sum of a number of resonances. So this is using a simple isobar model for them. We model these as Bright-Wigner states, which are interfering with everything else that is of a vector amplitude in the decay. So when we do that, then you get a plot like this one over here to the left. So this is a plot of the differential decay rate, B2K plus mu mu, as seen in LHCb from the data taking up until the end of 2012. So you see in this one here, more or less what we had before in this one here, you see the peaks here, in the J psi here and the psi 2s here. These peaks here are truly enormous. They reach something like 10 meters into the air when you're looking at your screen here, just to set the scale of this. So the penguin decay part that we're interested in here is really small in comparison to it. What you see also on this plot here is you see in the purple down here, you see how we actually get an interference between the different components in this one here. So one thing that we get as a result of this plot here is we get that the branching fraction is below the standard model expectations. If you remember before, I said that the branching fraction was effectively given as C9 squared plus C10 squared. And you see that very clearly in the plot to the right here. You see a plot here of the determined value we have of C9 versus the determined value of C10. And this here, these bands here basically form where we say that the experimental measurements, they lie somewhere inside this region here, which you can see basically forms a circle around 0, 0 because of this C9 squared plus C10 squared. The circle has a smaller radius than what we expect from the standard model due to that the branching that the rate is lower, the branching fraction is lower. You might ask in this particular analysis how we get any separation we only measure the rate, how do we get any separation between the terms, the C9 terms that are the vector resonances and the C10 terms that are the actual vector ones? And we actually get that from the interference that we get with the different vector resonances, because it's only the vector part that interferes with them. So in particular, actually, it's hard to see on this plot here because we have to merge bins together in this one here, so you can actually plot it in a visible way. But we actually get some sensitivity to distinguishing between the C9 and the C10 terms, in particular from looking at the interference with the phi resonance that we have sitting down here, where the size of the phi resonance is more comparable to the penguin terms. It's harder to get it from the interference with the decay because the decay is just too big compared to the penguin terms. So that was the easy decay. If we move on to the full kinematics, instead of looking at a decay like B0 to K star mu mu, then we have that now K star decays strongly to a K pi. So that means that we have a 4-body final state instead of a 3-body final state. So that means that we can parameterize the decay through 3 decay angles and 2 mass terms. One is the squared mass of the K pi system, and one is the squared mass of the dimuon system, Q squared, as we looked at before. So more complexity, but also far more information. So in general, the full distribution that we get depends on 6 complex Q squared dependent amplitudes. So you have those written down here. I cannot expect that you read the formulas here, but simply just notice the structure that we have in it. So you can see we have different combinations of the Wilson coefficients here. We have some where we add them together. We have some where they're on their own. This means that we get a separation power between the C9 and the C10 terms. We get a C7 term, which is no longer suppressed in the same way because we get a photon pole in it from that a photon can couple to the dimuon system. We get the form factors as we had before. Again, the form factors come together with the Wilson coefficient, so we have to rely on a theoretical determination of those. And then we also get what we here call the non-local hadronic contributions. So this is mainly the charm loop effects that we have here in this here. So it's a complicated prediction that we have here. The latest analysis from LHCb of these is based on data that comes from 2011 to 2016. One of the plots you can look at, and the plot has been mostly shown around, and you've probably seen in conferences and so on, is a plot of the what we call the observable P5 prime. So no need to go through the history of this name, apart from that you can imagine that there were 4 failed ones before it. But this is basically a derived parameter from the angular distribution. By measuring the angular distribution of the decay, you can determine this P5 prime parameter in a given bin of Q squared. It's designed such that the theoretical uncertainty we get is minimized. You can also see in the fit here that there are 2 gray regions in it. One corresponds to the DSI, one corresponds to the Psi2S. So this is what we call the binned analysis of this decay. And the idea is basically that we exclude the regions around the DSI and the Psi2S, where these charm loop effects will be the most dominating. So we basically just say we don't look there, and then we assume that the effect of those charm loops is very small elsewhere. What you then see in the plot here, look at the black data points, that's the combined data between them. You see that in particular in this region here, between 4 and 8 GeV squared or so, we see that the data points, what we returned in data, lies well above what we have in the standard model prediction here, including the uncertainties that we get from the best estimates we have of the form factors, the non-factorizable contributions, and the charm loops. And this is really what forms the basis for the disagreement between the standard model expectation and what we measure here. So there are many other experimental measurements. In fact, there's something like 125 different measurements made now. And what you can do with those is you can combine all of those into a global fit. So you take all the measured Reinstein fractions, you take all the angular observables, And for each of them, you say, what do they fit best with in terms of the Wilson coefficients? Most of these fits are phrased in terms of values to C9 and C10, the vector coupling and the axial vector coupling, mainly due to that that C7, that's related to the virtual photon, that one is very well determined from the inclusive B2S gamma decays and actually agrees very well with the standard model prediction. So if you look at these here, so to the left here, we have one of these fits here that's performed with a package that's called the flavour package with a research group around Straub. And what you see is different measurements that contribute to basically are compatible with experimental measurements for specific values of C9 again and C10 here again. Standard model again in these plots here is just rebased, so it sits at 0.0 in these here. So you can see there's a number of different measurements here, and they all come up with a compatible region that sits well separated from the standard model presentation here. So to the left, I'll come back to this plot later when I talk about cross checks and so on, to explain in more detail what's on it. You see different types of measurements, whereas in the plot to the right here, you see measurements from different experimental collaborations. So you see measurements from Atlas, from Bell, from CMS, and LHCb here. And you see that all of those are in agreement with each other, but of course that the measurements from LHCb are the really constraining ones at the moment compared to any of the other measurements here. So again, this here is with the best knowledge we have of the theoretical uncertainties, but nevertheless, it still has some uncertainty related to, do we really understand how big some of these effects are, since we don't have a method for calculating them from first principles. So that was the background, that was the theoretical language, that was the experimental measurements we have. So let's now try to look at how can we actually figure out if this is a real thing or if this is really just the standard model behaving in a way that we didn't quite expect it. And there are several directions we can follow in that, and I'll try to go through each of those here. So just a quick overview here. One of the things we can do, we can compare final states with different types of leptons in. We can compare different kinematic regions of a given decay. We can try to not determine the QCD effects, the charm loop effects, the non-factorizable things from the theoretical side, but we can say, well, can we just fit for them in the data? We can use dispersion relations, or we can look for CP violation in the case, and we can also exploit that there should only be one new physics. We cannot have one value of C9 in B2S-mu, and then another value of C9 in B2K star mu, because it's the same effective for fermion coupling we have in those two. So let's try to go through these here. So let's first consider what we can do in terms of final states where only the lepton differ. So lepton universality is one of the key features of the standard model. So the only difference for decays that have electrons, muons, and taus in them is basically coming from the mass. The effect of that is mainly just a phase space effect. It's easy to correct for that in predictions of measurements. So that means basically that the discovery of lepton flavor non-universality, the two different decays that only differ with if they have, let's say, muons or electrons in the final state, can be a very clear sign of new physics. However, there are some drawbacks of doing that measurement. So one of them is that while on the theoretical side, that leptons are universal in the standard model, from the experimental side, they're certainly not universal, whereby that I mean that they are not detected in the same way in our detectors. The other thing is, of course, that discovering new physics in this way, of course, only works if the new physics is not lepton universal. Otherwise, we'll just discover the same thing, and then when we compare them, it doesn't tell us anything. So let's quickly look at this, why it is difficult to do experimentally. The main problem for electrons is that they are very light particles. So this means when they pass through material, they emit bremsstrahlung. Then when they go through the detector, so if we have some bremsstrahlung that is emitted here, we then have a magnet here. Then when the particle bends in the magnet, it's actually lost some of its original momentum already. And that means that we measure the particle to have a lower momentum than it really has. This makes it difficult for us to reconstruct mesons, for example, because we no longer have the correct energy of the final states. Further on, we can have photons that can convert fake electrons. That means also we get much more background. We can do different ways of what we call Bremsstrahlung recovery to fix this, but it is certainly not as good as if the electrons were not so light. Muons, on the other hand, are the perfect particles for identification. They have no, or essentially no Bremsstrahlung because they're heavy, but the same momentum, the Bremsstrahlung is proportional to the mass to the -4, to the power -4, given that the muon is factor 200 heavier than the electron. 200 to the power 4 is a huge factor. It doesn't matter for muons. Muons are also stable within the particle physics detector. They fly through the entire detector. They don't have any strong interactions, so basically they're easy to identify as well. Taus, this is the only thing I'll talk about taus in this case here. Taus are even worse than electrons in terms of identification. They're short-lived, and then they always decay with at least one neutrino in them. So that means that if you have to have final states, for example, that contains 2 taus in it, you will get from anywhere from between 2 and 4 invisible neutrinos in your final state, which makes it very difficult to reconstruct them. So we want to make a measurement, for example, where we want to compare the decay rate of B-Kmumu to that of B-Kee. Standard model say they should be the same. But we've seen that experimentally, they are difficult to compare. It's difficult to get the efficiencies of these exactly right. So one of the tricks we can do is that we can form a double ratio as we have here. So what you see in this one here is you see up the top here, you see we have the ratio between the muon decays and the electron decays here. But now we form it as a double ratio with the decay that goes through the J psi here, and then the J psi decays to mu, and the same decay here where the J psi decays to EE. And the point is that we know that the J psi to mu decay and the J psi to EE decay, which is an entirely electromagnetic effect, we know that that one is lepton universal. So if we've got the efficiencies of our muon identification and the efficiencies of our electron identification slightly wrong, then that effect is effectively cancelling out, as you can see in the bottom part here. We can simply count how many we have in these different final states, and then we get some efficiency ratios here that we need to determine. But those efficiency ratios are no longer between muons and electrons, what is difficult to do, but they're between muons and between electron and electrons, just in slightly different kinematical regions. So that means that we can get a much better handle on our systematics in the experimental measurement. So what you see here is a plot of what we get in these decays here. So this here compares a plot here of how it looks like in the KEE final state. So this is B to KEE. We see the signal peak is what's in the black here, so the data points here. And we see that we have a fair amount of background in this decay here. In particular, we get background from what we call partially reconstructed decays. This is actually mainly B goes to K star EE that we see here. And we also see that the signal component has a very long tail here, which comes from the Bremsstrahlung as I talked about. So you might say, ooh, this looks really hard to separate the signal from the backgrounds here. But remember again, we had the same type of plot for the final state to the J psi instead. And there we have a factor 1,000 more statistics. There we can determine, and then it's more the ratios that we need to look at. When I said muons were easy, I meant they were easy. You have the B to Kmumu final state over here, which you can see essentially has no background in it. It's very easy to determine the yield here. If you look at the width of the signal distribution, then it's a bit of a cheat. The scale to the left plot is much larger than the scale to the right plot. So the muon peak is actually also much narrower than what we have for the electron peak. Having done all the cross checks for this, we can then go and look at what we actually measure. Remember that the theory said basically that the ratio between the electron final state and the muon final state should be 1. We can go and measure that. We call that ratio for RK. So the 1 here is the standard model prediction here. This is the measurements done as in bins of Q squared, so the invariant mass squared of our lepton pair here. And we see the LHCb measurement down here sits low with respect to the standard model prediction. We also see the measurements from Barber and Bell here that have significantly higher uncertainty in them. If we go and do exactly the same in the K star final state, then we have 2 measurements here, different Q squared regions, which are also sitting well below the standard model prediction here. So what we have here is kind of a bit of a reverse situation to what we had in the decays I've talked about so far. Here we have that the theory predictions are very, very clean, but we have some underlying, concerns about, do we really understand the comparison between electrons and muons here? So I think that there's 2 things required before we can make firm conclusions for this. We need more data. The significance we have of divination here is only at the 2 to 2.5 sigma level, could just be a statistical variation, but we also need another experiment to do these measurements. And Bell 2 would actually be an excellent experiment for doing that. They have electrons and muons are behaving much more in the same way at Bell 2 compared to LHCb. So that will be very exciting in a few years' time when there'll be measurements coming on that. Okay, let's continue our tour of looking at ways that we can potentially distinguish between QCD effects and new physics. So one of the obvious things is that new physics should affect all regions in Q squared in the same way. We can't have 2 different values of C9 for low Q squared and high Q squared. Remember, this is an effective theory. We're not sensitive to the exact kinematics of it. We're just sensitive to the type of the coupling we have and the strength of the coupling. So one of the things we can do is we can actually take the data. We looked for the observables before, the P5 prime observable, etc. We can take that and we can look at each of the bins in Q squared. We can look at what value of the vector coupling C9 would that correspond to. Now, of course, we are slicing our data here, so we're losing in statistical precision, but nevertheless, we should get values which are in agreement. And that's exactly what you see in the plot here. And we see that these here are 1 sigma bands we have here. We see that all of these here agree with a single, that they're taken from the same value of C9 here. That could, of course, you could invent a trend here. There's nothing significant in that. But that's one of the things that we would look at with more data. That was one of the things that would indicate that there's something going on we're not understanding if we saw that this C9 value was changing as a function of Q squared. One of the things that's very encouraging from this is actually that the data points we have down here and the data points we have up here, this here is very much relying on lattice QCD. This one down here are relying on light count sum rules, and we see that they agree. That's a very nice cross check. Next one up is the data-driven methods. We already looked at this one before. These are the amplitudes that describe the B to K star mu decay, the 6 complex amplitudes that describe it. And we can say, well, why don't we just try to fit for it all? Let's rely on that we have a parameterization of everything in it. So that in particular means the non-local hadronic contributions here, this one here, and that comes here. We need a model for this, the ugly part, as I call it here. So the model we're using is one that's quite similar to what's been used for the B to K mu decay. So we model the vector, the charm loops we model as a sum of vector resonances in it. And then we also have to model the contribution from the dipole form factor. That's what we have here. So this is kind of an effective C7 component we get here in this one here. So all of these here comes with a bunch of unknown numbers. How much do we have of each of the resonances? How much do we have of this effect here? What are the relative phases of all of this here? But we say, well, we'll just fit for it all. We need more data, but we'll just fit for it all. So what we do in that is where we include then, in terms of vector resonances, we include all the vector resonances that we know about be involved in this decay here. Phi, the rho, should have put in the omega here actually as well, J psi, psi 2s, and the higher side resonances as well here. So we can then take this model and we can at least try to compare it to what other things has been done on the theory side. That's what's done in this paper here. So what we did in the plots you can see over here, the purple band you can see in this one over here is basically a standard model prediction, and then including what they in the paper of the Flavio authors say is the uncertainty coming from these non-factorizable contributions and the Chandler contributions here. And we can compare that to, in the model we have here, the isobar model as we call it, how big variations can we get on the standard model prediction when we vary these parameters, we vary the phases we have between the different vector resonances and so on. And that's what gives you the cyan bands here. And we can see that we get a very good agreement, different observables here, in terms of the regions that we can cover. In some of them we have some more flexibility than we have in others. If it's data driven, that's fine. We will just determine what the parameters are. We've already shown for B plus to K plus mu mu that this is a viable approach and we can get a good fit to data. And this is work in progress. So I'm not going to show you any results from that, just say that it's well in progress, the analysis from that. It has a number of challenges to it. We fit everything here in a completely unbinned way. That means we need to understand what we call the acceptance. We need to understand all the efficiencies in terms of all the angles in Q squared. We need to understand the resolution. Particularly, we need to understand the resolution that affects how the very, very narrow J psi peak is spread out in our measurements. And we also need to understand backgrounds very well. We need to put in a veto on B to K mu mu decays, where we get a random pion that makes it look like a B to K star mu mu decay. And they cause a distortion in our sideband that we have to deal with. These are all issues that we have to deal with experimentally in order to be able to make the final fit that then tries to simply determine what is the QCD contribution to these decays, rather than relying on a theoretical prediction of them. Next one up is that we can rely more on the theory instead of relying less on the theory. So there's some promising progress and work that utilize that the scattering from the initial state to the final state is described by an analytic function in the complex plane. And we can use that basically to make a parametrization of the decay. We can calculate the 4 fermion coupling in a different kinematical region. Then we can utilize that as an analytic function and then get up to, determine what it should be in the region where we have an interest in it. I'll not go into too much detail of that, but simply if you look at the plot down here, then the physical region that we are interested in sits over here to the left in this plot here, whereas the place where you can make the theoretical predictions with much lower theoretical uncertainty sits over here on this plot here. This actually, in terms of the Q squared variable, this actually corresponds to negative Q squared values. So it's effectively a scattering effect we are calculating here instead. Think of it as a deep inelastic scattering we are calculating here instead. And we can do that with much better precision. Then we can fit these theoretical points over here, and that then gives us a prediction in the region over here, which is the region that we are interested in. So that's a way that we can link together a theory prediction in a different kinematical region to where we will need it. The almost final one I will cover in terms of different ways we can look at things is we can look for CP violation. We know that QCD is CP conserving. So if we see CP violation in any of these decays here, then it has to be caused either by the weak coupling or by new physics. CP violation in the standard model we know very well now. So we can predict the direct CP violation that we will see in B to K star mu mu very well. It turns out that it's incredibly small due to the CKM factors that are involved. So small that we will not have any hope of seeing it. So that basically means that if we see CP violation, then it will be also a very safe sign of that there is a new physics contribution, because it cannot come just from the chart waves. However, to observe direct CP violation, we need to have 2 different amplitudes that are interfering. And those two different amplitudes need to have different weak phases. That's the CP violation we're interested in, but they need to have different strong phases as well. This is well known for measuring direct CP violation in many other decays. However, there's no reason to expect that the standard model penguin amplitude and the new physics that we might have, there's no reason to expect that they would have different strong phases. So what we can do instead, we can actually say, well, rather than being scared of the charm resonances, we can actually utilize them. Because we've got resonances here, that means that we will have a phase shift when we go across them, meaning that we have a strong phase that's changing quickly. So at some point close to the charm resonances, what you can see in these figures over here are kind of plotting out how would these direct CP violating observables we have here, how would they vary when we're changing the weak phase of some possible new physics contribution. And you can see you get a wide variation of these when you're close to the value of the J psi mass squared, which sits just at this point here. So by going close into the resonances that we otherwise regard as a nuisance, we can actually increase our sensitivity to new physics contributions that are CP violation. So this looks like a very interesting avenue to follow. It has to follow on from the data-driven approach I talked about before, because we have to utilize the methodology from that one. And of course, again, this only works if there actually is any CP violation in new physics. So the final one of these I wanted to cover here is basically to exploit that there's only one new physics. So I promise to get back to this plot here that you can see here. So for a given 4 fermion coupling, there should only be one type of new physics. So if we look at the coupling Bs-mumu, so that's the one that we have in B0 to K star mu, it's the one that we have in Bs to mu, the one that we have in Bs to phi mu, lambda B to lambda mu as well. All these decays are governed by the same 4 fermion coupling in our effective theory. So therefore, if we determine what are the Wilson coefficients from that, we should get the same result from all of them. And that's exactly what's attempted in the fit you're seeing over here to the left here, to the right here. So for example, if we look at the branching fractions, how many do we have of the B to K star mu, B to K plus mu decays, then we get that that gives us a constraint that sits like this here. Again, notice how this is kind of part of a big circle. That's again from basically the C9 squared plus C10 squared effect. The branching fractions are lower than what we expect in the standard model, so we move closer to the 0 point that sits somewhere up in this direction here, and this one here. Then we can then look at the Bs to mu branching fraction. The Bs to mu branching fraction is only sensitive to C10, it's only sensitive to the actual vector coupling, so we get a band for it like this here. We can look at the angular measurements. How do the particles distribute the K pi and the 2 muons and B to K star mu? That gives us a constraint like this here. Very nice to see how that constraint is orthogonal to the constraint we get from the branching fraction. And then we can take all of it and combine it. The combination of all this gives us the orange region here. What's the point I wanted to make here is not so much that this point sits away from the standard model prediction, but more that all these different things are actually compatible with each other. If these different regions did not overlap, then it would really be a sign that there's something we do not understand in the calculation, rather than it is an effect of new physics. Again, you can see here that more data would obviously be good for this. We would like to be able to shrink each of these bands more to see that they still sit in the same region. This is very much the same game as what's been played in looking for CP violation in the standard model, where you have seen the plots over the years that shows a very good compatibility with that the CP violation we observe is only governed by the standard model, as in that the fit to the unitarity triangle fit with a single point in that plane. So final point here, which is about direct searches. If we have new physics out there, then why haven't we seen it at the LHC? So we can try to make a very naive estimate of what are the masses involved in this. So in an effective theory, we will only be sensitive to the coupling squared over the mass squared. So if we have a larger coupling and a higher mass, then it will give us the same effect. So what we can basically say is that the best fit values that we've determined, right, if we take the best fit value we have in the plot here, the orange region here, if we take that, that basically gives us amplitudes which are about 20% of the size of the standard model contribution. We can then ask, how big is the standard model contribution? That's basically given by the expression here. Loop decays, we've got a VTB, VTS, from the coupling, from the quark transitions in it, 1/16 pi squared here from the loop. So we get an expression like this one here, plug in the numbers in this one here, and that basically gives us something like 1/30 TV squared. That is if the effects of thermal physics are happening at tree level. So we basically say if the coupling is 1, then we would get these kind of effects from a 30 TeV particle. If, on the other hand, we say that our model is a minimal flavor violating model, so where the new physics follows the CKM structure, something that's been used as a way of explaining why we haven't seen new physics in K and decays already, for example, then what happens is effectively that these CKM factors here, they drop out. Otherwise, it's the same calculation, and we get that the new physics effect should happen at the order of 6 TeV for lambda over the mass. If the masses were to be that high, then it's obvious that we have not seen it at direct searches yet. But of course, if the coupling is lower, then the mass will go down of where they should be. In general, for these here, the limits that we have from the LHC sits in the 1 to 2 TeV region, depending on exactly what you're looking for. So back to the question, can we disentangle new physics and heavy flavor decays from QCD effects in the standard model? So do we need more data? Yes, definitely we do. And we need it mainly to be able to make many of these cross checks that I highlighted later, do fits where we fit for the QCD, split it up into different regions, looking at the lepton flavor universality. All these require more data in order to be doing well. Do we need more theory? Definitely, yes, as well. I didn't talk about some of the theoretical issues that are involved that are still hanging about there. One of them, for example, related to that the theoretical models at the moment basically assume that the K star is a stable resonance, what we call the narrow width approximation. It looks like there's progress in that we can see what the effect will be in that. There might be work coming out, lattice QCD in that. So yes, definitely more and better theory. And give up, I think I've given the answer to that one. No, not at all. I think there's a way forward to understand this better, but it will take time. So I hope this basically is my conclusion. This here is basically the answer to the question I've begun with. So with enough data, we will be able to distinguish a new physics contribution that we have depicted here to the left from the charm loop effects that we have depicted here to the right. So thank you very much.
Thanks. Thank you very much, Ulrik, for very, very clear and
good. Thank
very,
you.
very interesting talk.
It's always good when you give a seminar that somebody says something at the end and you haven't spoken to nobody for half an hour.
Hopefully one of us would have noticed.
Yeah.
So let's throw this open for questions. So either put your hand up or feel free just to unmute and ask a question. Do we have a first taker?
Oh, if can I ask first question then?
Yeah, go ahead, Artyom.
Yeah. Say yes. Thank you first of all for a very, very clear and informative talk. So you're talking about various cross checks and so on and so forth. I mean, we're going to go forward and identifying whether this is really a signal of new physics or not. But looking at this, and I think it was at page 29, you were talking about the Q-square dependence of these Wilson coefficients, right?
Yeah, this one here.
Yeah, and maybe I didn't understand quite clearly, but you mentioned that this should be universal in a sense across the Q-square. Yeah. What do you mean under that? Because
I mean that's the value that we can determine what, if we look at the decay in low Q squared, we can say, in order to make the measurement we make, what value of C9 would we have to give us that branching fraction or that angular observable or whatever. So if you look in the very lowest bin of that, it basically says, well, for that to match up, the new physics contribution to C9 would have to be somewhere between -1 and 0.8 or whatever. Then we can do that game in different bins of Q squared. But of course, this C9 value, this is the new physics C9 value, has to be the same everywhere. It's the same effective theory we have. So if the box at the end was sitting up at +2 instead, then that would be a real sign that there's something going on that's wrong. We would expect these to be compatible with a straight line, effectively, not a straight line, at the same value, a constant value in C9.
Yeah. Yes. Okay. So well, maybe for that region of Q squared, that should be roughly the same. But this C9 is in any way is a running parameter. It should have some at larger Q spread the dependence on Q squared.
That is taking into account. So the value when we talk about C9 here is we talk about the value at the W mass actually.
Oh, I see. So it's,
sorry, I should have said that. So all this here is the value of C9 at the W mass, and then you take into account how it.
Okay. So can I have a related question as well?
Yes, of course you can.
You were obviously talking about that. This C9 has to contribute to other processes as well, and go with a cross check with that. But again, unless I misunderstand something, but obviously you can't have just C9 per se, because this is effective theory. But if you go to and compute the kind of radiative correction to this,
yes,
that the most probably generate other operators as well.
Yes, they will.
Other processes as well.
Yeah.
Maybe in high energies or at low.
Yes. No, I completely agree, and that is of course one of the weaknesses of having just an effective theory like this, is you can come up with results that don't have any solution, if you like.
What I'm saying is that if you have, for example, if you believe that this is a new physics result, you can kind of extract that coefficient, and then you can compute the theoretically at the high energies. What type of processes you generate, assume that this is a real effect, and go to check also those processes in principle. Cross check with those. Of course, there is a theoretical bias in that, but anyway.
Yeah. No, you can. I'm not entirely sure if I understand your question, but one of the things is that you will from this here, for example, get effects in B0 bar mixing as well. So anything you put in here will through the mixing of the coefficients will give you a result in the 4 fermion coupling that's responsible for B mixing as well. Yes, so that puts a constraint on it. And it is actually folded into one of the plots, sort of as a tiny comment somewhere, I think, on this one here. If you look at this one here, the top band actually says Bs-mumu and delta F equal 2.
Okay.
This one here takes the constraint from B mixing into account as well.
Okay. All right. Thanks.
Okay, there's a comment, I think, in the group chat, which is just a presentational suggestion from Peter on the same point that was confusing Archel. I think, Mikhail, you were next, I think, with your hand.
Okay, let me unmute. Okay, I have one question to that RK measurement of last year. So if I remember correctly, when looking at the paper back then, there's also in the supplementary material, there was a separate analysis for the 7 and 8 TV data and the 13 TV data.
Yeah.
And the 13 TV data, if I remember correctly, was consistent with the standard model, while it was mostly driven by the 7 and 8 TV data. Can you comment on that, kind of how that lays together?
Yes, I can comment on it, but not say too much about it. It is completely true that the value that we measured in the 2016 data is closer to the 1.0 value of the standard model than it was in the previous one. You can ask if the two data sets are statistically compatible with each other, and they are a bit more than 1 sigma apart, 1.5 or something like that. So there's something like, you know, a whatever 30% probability that if you randomly took these from a big data set, it would split like this. So they're compatible, but nevertheless, yes, we of course look at it and say, oh yeah, that's interesting. Luckily, we are quite far in the progress of adding in the 2017 and 2018 data as well. So we should actually double our data set as well in an analysis that I would hope come out during this year.
Okay, Bruce.
So first of all, Ulrik, thank you very much for the talk, which was excellent. Can you just go back to slide 36, the one that you were speaking to just earlier?
Yeah.
Yeah. So you have a sensible list of processes there where one should be able to make equivalent measurements. I mean, you partly answered this question with the reference to constraints from B-mixing, but if this is being described by a Bs-mumu for fermion interaction, while I agree those three things there are the first additional things you would look at, there's a very long list of processes that you could insert a Bs-mumu for fermion interaction into if you've got creative.
Yeah.
I mean, anything with a photon of high enough virtuality would even be enough.
Yeah.
So I know this sort of takes it beyond LHCb, but do you know how thorough the study has been on this? Whether there are auxiliary measurements that could be made elsewhere to
no,
test, or predictions that might be made by that best fit point, for example?
Yeah, no. There is certainly an active area, but no, I'm not aware. I cannot point you to a paper that has a long list of these. You should look at this. I suspect that in many cases, unfortunately, in other decays, it will drown out in QCD uncertainties the effect that might be there, because there you're looking in general. You would look at a suppressed effect there. So here we try to look at a place where this effect can be the largest possible, and in other places you would get in a suppressed way. So, but no, it is an interesting thing, because that's of course always the game we play when you come up with a new physics model. Is it already excluded by something else? Yes.
And in terms of future facilities, I mean, if you had a muon beam that was sufficiently bright, I mean, there's strangeness in ordinary matter at sea level. You scatter neutral current scattering of a muon off.
Yeah, actually one of the extremely interesting measurements you could make, if you're allowed to think in hypothetical ways, is that you could look at mu plus mu minus to produce single BS stars. Yeah.
If you had a collider, I mean, which is even more remote.
That would be an extremely clean measurement to do. So there was a very interesting paper from Ben Grinstein and Jorge Kamalik on that idea. They considered if it could be done at Bell effectively, but the energy spread for any plus or minus is far too big that it's viable.
Right. Thank you.
Do we have some more questions? Any more hands? Maybe just one, Ulrik, the evolution of the RK and RK star measurement, so that you've got the sort of 2.5 sigma discrepancy at the moment. And obviously you've got more data in the can, but you've got upgrades and things coming up, etc. How is that expected to sort of change over time, the significance that one can reach as LHCb sort of evolves?
I didn't include the table of projected future measurements, but with if we take it all the way to the LHCb upgrade 2, then we will get effectively a factor 100 more data than what we have in the results I showed you today. So, you know, from a purely statistical point of view, the uncertainty should go down by a factor 10.
Yeah.
That is optimistic, I would say, because the most challenging thing in upgrade 2 for LHCb is to get a performant calorimeter. So therefore, it will be a real challenge to keep the efficiency for the electron final states the same as we have at the moment.
Mm. Okay. Looks like Bruce has got a comment or a question on that point.
Yeah, so again, just going perhaps a bit beyond LHCb at this point, Ulrik. I mean, you showed the mu versus EE comparisons, which looked very difficult, with no offence to LHCb. I mean, is that, bearing in mind that LHCb will always ultimately win on statistics, except in very special modes?
No, that was why I explicitly put in Bell2 on that slide.
Is mu versus EE the place where Bell2 is most likely to make a contribution in this area, in your opinion?
No, I don't think so, actually. I think it can make really a big impact there, but I actually think there's one place that's even more interesting and potentially is available earlier, which is a measurement of B-K star and 2 neutrinos.
Mm-hmm.
In many of the physics models, this decay have a much larger branch refraction than in the standard model. The limit is still quite poor. LHCb is a lost cause for doing that. So I actually think that's the place where, you know, if the stars were aligned correctly, that's the place where Bell2 could have the first impact. And anything with a tau in, you know, B-K tau mu or B-K tau tau, whatever, Bell2 will win in those eventually as well.
Right, but in those, one is getting into more debatable model projections about the relationship between modes.
Exactly, and I also think that actually B-K tau tau, if I remember correctly, even for Bell2, it will be difficult to see that one at the standard model level.
You know, that's interesting. Cheers.
Any more? I'm aware at the time I've been a chair that's, I've indulged the discussion, not the speaker, who kept pretty well to time. So, do we have any other questions before maybe we call it an afternoon? I'm not seeing any. What do we normally collect our slide? Do we normally ask for the slides? Archel, Mikhail, what is it?
Yes, usually I ask if the speaker is happy, if Ulrik would be happy. We put it